Section 9.2, equation of a plane, obviously in 3 dimensions. So here's a picture of a plane. You've got a point A. So in order to describe a plane, really you need to get to that plane. So you need to have one point on that plane, and then in order to get to any point on that plane from point A, you need to have 2 direction vectors B and C. Those direction vectors will allow you to get to any point whatsoever. So for example, let's say this point here, you could go along B, and then maybe if you add 2 lots of C to that, you'll get to that point. Okay, so a combination of B and C from that point A will take you anywhere you like on that plane. So if you write it down, you've got to have get to the plane, which is described by the position vector of points A. So you need to have a point, and then you need to have 2 vectors, 2 direction vectors, and you will be adding a combination of those, multiples of those. Those vectors cannot be parallel to each other, and obviously those vectors need to be within the plane. There you go. So this is the equation of a plane that you need to remember. So this is a vector equation of a plane. So let's see how we can use this equation. So this is quite a common question, quite a nice and easy. You've got 3 points. Through any 3 points in 3 dimensions, you can draw a plane. So now let's find the equation of that plane. So imagine this is our plane. You have point A, point B, and point C. So you need to use one of the points. So the starting of your equation is going to be, you can use the position vector of point A, position vector of point B, or position vector of point C. It doesn't matter. I'm going to go for A. So you will start with point A, 2, 2, minus 1, plus, and here we're going to do multiples of, so lambda lots of one of the direction vectors, and I'm going to pick AB. So that's going to be, let's say, one of my direction vectors. And then I'll pick AC. There you go. So my AB is going to be D1, and AC is going to be D2. So let's find this. So it's going to be B subtract A. So B was 3, 2, minus 1. Take away 2, 2, minus 1. So it's 1, 0, 0. That's the first direction vector. The second one, it's a position vector of C, which is 4, 3, 5. And you're going to be subtracting position vector of A, 2, 2, minus 1. And the answer you're going to get is 2, 1, 6. So let's put those direction vectors here. So it's going to be lambda 1, 0, 0 plus mu 2, 1, 6. I prefer vector column vectors. If you want to write it in IJK notation, it will look like this: 2i plus 2j minus k, plus here you just have lambda I, and you will have 2, oh, let's put mu outside, 2i plus 3j plus 6k, or you can expand it. There you go. Let's look at example 8. So in this example, we are asked, we've got a position vector of point P, 2, 2, minus 1, and a plane pi, capital Pi, r equals 3, 4, minus 2, etc., etc. We need to show or verify that this point indeed belongs to that plane. So what we're going to do, we're just going to substitute instead of r the 0.22 minus 1 because it needs to satisfy our equation. So it's 3. You can put these components together, plus 2 lambda plus mu, 4, 1 lambda minus 1 mu, minus 2, 1 lambda plus 2 mu. You're going to have 3 equations. We're going to pick 2 equations, solve them simultaneously, find lambda and mu, and then substitute those solutions into the third equation to confirm that it will work for that equation. So using equation I and II, rearranging it first, we're going to get 2 lambda plus mu is equal to minus 1, and lambda minus mu is equal to minus 2. Adding them together, I'm going to get 3 lambda is equal to minus 3. So lambda is equal to minus 1, and mu is going to be equal to minus 1 minus 2 lambda. So that's minus 1 plus 2, so it's 1. So lambda minus 1, mu 1, sub into equation I. Let's see what we get. Minus 1 is equal to minus 2, lambda is minus 1, mu is 2. So I'm going to get minus 1 is equal to minus 1. So it is verified. You could say that P belongs to that plane. Cartesian equation of a plane. There you go. So we've met the vector equation of a plane, and here's the Cartesian equation of the plane. We'll talk about it a little bit more in the next section, but really this is what it looks like. So you've got ax plus by plus cz is equal to d, where vector a, b and c, so if you take the coefficients of x, y, z, it's called the normal vector. So we'll put n, always little n, that is the normal vector to the plane. So that means it's perpendicular to the plane. So over here there's my vector n. See, it's perpendicular to the plane. So we're going to have a go at example 9. We are asked to find a Cartesian equation of the plane with the normal vector being 3i minus 2j plus k, and passing through a point with coordinates 8, 4, minus 7. So once you've got the normal vector, that allows you to create the left-hand side of your equation. You just need to take the coefficients of the components, x, y, z components of your, sorry, that's minus 2 y and then plus 1z. There you go. So you already have half of the equation. So we've taken the x, y, z components of your normal vector and put it as coefficients of x, y, z in the equation. Now we need to find what d is. So you're going to substitute this point, because these are the coordinates of that point. So we can substitute the coordinates into the equation because they have to satisfy this equation. So 3 times 3 minus 2 times 4 plus minus 7. That's what our D is. So it's 9 and then minus 12, no, minus, sorry, 9 minus 8, so it's 1, minus 7, this is going to be minus 6. Let me just double check if I done it right. 9. Well, I'm just check. For whatever reason, I've put 3 here. That's 8. That doesn't make sense. Yeah, so it's 24 minus 8 is 16 minus 7. That's better. That's going to give me 9. Yeah, that's better. Okay, so what is the overall equation? Let's put D into this above equation. There you go. Okay, so if you've got an equation like this, you know straight away that A, B, C will represent a vector that's perpendicular to that plane. And then if you know what that is, that vector, like over here, you can just create the left-hand side and then substitute the coordinates of a point that you know belongs to that plane to find the value of D. So off you go and do exercise 9B.